Okay, we're just going to do the last video now on redox chemistry. This is for the week that basically I'm away and you're away a little bit. So it's the third video and the final video in this. You've got a booklet to be working along with as well from Chem Sheets. So basically, let's just do a little recap of what we've done so far. So I've introduced the idea that there are lots of chemical reactions out there called redox. They involve the loss and gain of electrons, right? Loss and gain of electrons. In a redox reaction, one species, one thing will lose electrons and another thing will gain electrons. I've introduced the idea of oxidation states, where you can find out effectively how many electrons an element has got within a compound. It's a strange way of saying it, but for example, if you had CO2, the oxidation state of the oxygen is -2, so effectively the oxygen has got 2 extra electrons, or each oxygen has got 2 extra electrons, and the carbon in here is +4, which is a bit like saying this carbon atom is effectively lost 4 electrons in this compound, or has got 4 electrons fewer than it normally has. So oxidation states are useful. Another skill that we've learned is how to write half equations. So they can be as simple as this. When copper turns into copper 2+, you can balance that half equation by balancing it with 2 electrons. So this is a 2 electron loss, so a 2 electron oxidation. Or they could be complicated, where we say things like this: MnO4- can turn into Mn2+, and they might say balance this half equation, in which case you would go balance the oxygens, 4 H2Os, balance the hydrogens, 8H+, balance the charges. Well, this side is 2+, this side currently is 7+, so I'm going to need 5 electrons on here. So these are half equations, and this is a half equation that says when copper turns into copper 2+, it loses 2 electrons, and this is a half equation that says when manganate MnO4- turns into Mn2+, it gains 5 electrons. So these half equations are pretty useful. I'm just going to show you this. 5 electrons are gained. That shouldn't be a surprise, because the manganate in here has got an oxidation state of +7, and the oxidation state of here is +2. To get from +7 to +2, you gain 5 electrons. So it does all link up. And these links will you'll get better and better at seeing as you go through chemistry. The main aim for today is what we're going to do is we're going to start to combine half equations. So if you know the reaction that copper becomes copper 2+ by losing 2 electrons, and you know separately that manganate can gain 5 electrons and form Mn2+, these are 2 half equations, and we can combine 2 halves together to make a whole equation. So I'm going to come back to this example maybe later, but we could, in theory, combine this half equation with this half equation to make an overall equation, and that's going to be the aim of today's lesson. All right, I'm going to come back to this one in a minute. Right then, so when we're combining half equations, I'm going to go actually straight onto the task that you've got. It says 2 half equations are added together so that the electrons cancel out. You know what? I'm going to go back to my example straight away. Just change my mind. All right, so if we know we have a chemical reaction that is between copper and manganate, and we've got these 2 half equations. In other words, we know that copper will form copper 2+ and manganate will form Mn2+. And I've written these 2 half equations. These can be combined into an overall equation. But the first step, what we have to do, is make sure that the same number of electrons that have been lost are the number that have been gained. They have to be the same. So currently 2 electrons lost, 5 electrons gained. That doesn't work. But both 2 and 5 go into the number 10. So if I times everything in this equation by 5, what would I mean? 5 coppers, 5 Cu2+, and 10 electrons. And I times everything in here by 2, that's to make my electrons 10. 8 becomes 16, this becomes 2, this becomes 2, this becomes 8. What we'll notice now is 10 electrons have been lost, 10 electrons are gained. So these electrons now cancel each other out. This is going to be the main thing we're doing today. We're going to cancel out these electrons. So the overall equation, I can now combine these two because the electrons cancel. It is 5Cu plus 16H plus, 16H plus 2MnO4 minus, that's this one and this one. I've used everything on this side, becomes 5Cu2 plus 2Mn2 plus and 8H2O. What you've got yourself there is a perfectly balanced chemical equation, and it came about by doing and balancing some half equations first. So this is an overall equation that has combined two half equations together. Quite a neat little trick that's going to be very, very useful towards the end of year 12 and into year 13. So what you've got here for this task is you've got some half equations that have been given to you. You don't need to balance them, they've already been done. So this is the one I've just used, MnO4 minus 8H plus 5 electrons. This is a 3 electron gain, 3 electron reduction. This is a 2 electron oxidation, a 1 electron and a 1 electron. So your task is choosing the correct half equations to write an overall equation. So I'll go through the first, well, I'm going to go through them all like I have done previously. I'm going to go through the first two as worked examples, then you should really pause the video, do the rest, and then check you're working. All right, so look at the following half equations. Use these to create the redox equation stated below. So, once I'm just going to pause. All right, so oxidation of Ce3 plus by acid, that just means acid, H plus, and manganate. So I'm going to choose the half equation this relates to. Ce3 plus must be this half equation. Oxidation of Ce3 plus, that's Ce3 plus becoming Ce4 plus, by H plus MnO4 minus, so that must be this one. So the question, interpreting the question, it wants me to combine this half equation and this half equation. So I'm going to just write them out first. That's my first job. It's a bit tedious, but I'm going to do it. MnO4 minus plus 8H plus 5E minus makes Mn2 plus 4H2O. And the other one is this, Ce3 plus makes Ce4 plus an electron. All right, if we notice this, we're going to look for the electrons. This is 5 electrons being gained, and this is 1 electron being lost. What you've got to do is balance the electrons. So that would require me to multiply the bottom one by 5. Don't need to do anything to the top. So look, 5 of these, and 5 electrons. I've now got 5 electrons being gained, and I've got 5 electrons being lost. So this is tick. This is good. I balanced the electrons. Now what I need to do is combine the half equations. So that's going to be MnO4 minus plus 8H plus now it's 5 Ce3 plus makes Mn2 plus 4H2O and 5 Ce4 plus. 5 Ce4 plus. Please ensure that you don't include any of the electrons in the overall equation because they've cancelled out. All right, that's the process. It's not particularly challenging, but I'm going to do another one just in case you want a bit of help. Okay, just going to focus this camera a little bit. It's not quite crispy. There we go. So now I've got oxidation of H2O2 by H plus MnO4 minus. Right, that's H2O2, that's this one. So I'm going to write that equation out, or sorry, that half equation out. H2O2 becomes 2H plus O2 plus 2E minus. So that's 2 electrons being lost. That is a 2 electron oxidation. Remember, oxidation is loss. So listen to me saying that. I'm writing this half equation. I can see this half equation is a 2 electron oxidation. The other half equation is the same one as before. MnO4 minus plus 8H plus 5E minus makes Mn2 plus 4H2O. It's this one that I'm pointing up here. I've just written it down there. All right, first job is to balance the electrons. This is a 2 electron oxidation. This is a 5 electron reduction. We've just seen this one in the example I did separately. 2 and 5 both go into 10. So if I multiply everything in the top by 5 and multiply everything in the bottom by 2, we're going to get there. I'm just going to write over this. So I'm going to put 5 there, 10 there, 5 there, 10 there. And on the bottom, I'm just going to go 2. I'm going to scribble over this 8, number 16, 10, 2, and 8. I know it's messy, but it works. All right, overall equation, stick an arrow in. I've now got to combine. There are all my reactants that I'm circling here, and they are all of my products. 5H2O2, 2MnO4 minus, 16H plus, which just means acid, makes, interesting, 10H plus, 5O2, 2Mn2 plus, and 8H2O. And you might well be thinking you've finished, but there is one more step. So if you just blindly listen to this and just be careful. Question 2, you haven't got it right until you've done one more thing. If you notice here, I've got H pluses on both sides of the equation. You're never allowed to leave that as the case. If I've got 16 H pluses here and 10 H pluses at the end, you need to cancel these out. I'm going to get rid of 10 from each side. That will mean there are a total of 6 H pluses on this side. All right, you have to cancel out anything that you find on both sides of the equation. Watch that video back if you didn't understand it, but that's the last step. All right, I'm going to go through the rest of them now so you know the answers. I might not go through them all in this much detail. I might just write the answers. Maybe. I haven't decided yet. Anyway, pause the video there if you want to carry on with these on your own. I'm just now going to crack on. All right. So question 3, I'm going to be combining this half equation, C2O4, and it's the same one again, H plus MnO4 minus. Right. Oh, I feel like I need to write them all out in detail, but I'm not going to. Right, this is 2 electrons versus 5 electrons, so I'm going to double everything here, times everything by 5 in this. I'm just going to do it like that. Right, 2MnO4 minus plus 16H plus, just double everything up there, plus, and then 5 C2O4 2 minus. There are all my reactants done. 1, 2, 3. The products are going to be 2 Mn2 plus, because I'm doubling everything in there. 8 H2O, because I'm doubling that. 10 CO2. I hope what you're noticing is I've just balanced a really complicated equation by using half equations. It might not seem like a really useful thing now, but I promise you it's brilliant. It saves so much time later on. In different topics. All right, oxidation of Ce3 plus by this iron oxide ion in acid. So that's this one here, which is 3 electrons and Ce3 plus. Right, what I'm going to do, I'm going to times everything in the bottom one by 3, and that'll mean I get 3 electrons here and 3 electrons there. So that should be easy enough. So it's 3 Ce3 plus. FeO4 2 minus, 8H plus, it's squished in here, isn't it? 3 Ce4 plus, plus Fe3 plus, plus 4 H2O. It'll balance, you know, it really will. 4 H2O, that's 8H plus, that balances. One ion over there. 3 ceriums, it all balances. How many more of these are there? Right, 2 more to do. Oxidation of H2O2 by this iron thing again. I'm going to write the 2 half equations out because I've run out of space on there. You can't see up there now. So H2O2 becomes 2H plus plus O2 plus 2E minus. The iron one, FeO4 2 minus plus 8H plus plus 3 electrons makes Fe3 plus plus 4H2O. Okay, I'm going to balance these. 2 electrons and 3 electrons both go into 6. So I'm going to times the top one by 3 and the bottom one by 2. That'll be 3 of these, 6 of these, 3 of these, 6 of these, 2 of these, 16H plus, 6 electrons, 2 of these, and 8 H2O. I'm going to need to cancel some stuff out. So it's going to be 3 H2O2, done that, plus 2 FeO4 2 minus, done that, plus 16H plus, done that, makes 6H plus, done that, plus 3O2, done that, plus 2 Fe3 plus, done that, plus 8 H2O, done that. Final checks, anything that cancels, yes, 6H plus, 16H plus, scribbly dibbly dibbly, 10H plus on that side. Whew, all balanced. I can't be bothered doing the last one, but I think you should be able to do that. Right, that's that task. You need to do that task and mark it. The next thing that you're going to do, all right, you've got to do this section called more redox reactions. This is like the overall pièce de résistance, resistance, if you say with a French accent. What we're going to do now is we're going to do some overall equations. Right. So what they're going to ask you to do, they're going to ask you to write a half equation, write a half equation, write an overall equation. It's quite nice. It's just the full thing together. So write a half. So I'm just ready to start now. What you're going to do? It's going to be an arrow in each box, isn't it? It's a really nice little activity, this. So converting bromide ions into bromine. I like talking through the proper words when I'm doing this. All right, bromide into bromine. It's good practice. These are bromide ions with their full outer shell. Anyway, balance the bromides. Stick 2 electrons on this side. That's that half equation balance. That was a skill that you did last time. SO3 into SO2. Sulfurs balance, oxygens don't, so I need to put a water on this side, H2O. Now I've got 2 hydrogens, so I'm going to put 2 H pluses, and that means I'm going to need 2 electrons on this side. Next bit, 2 electrons, they're already balanced. So the overall is 2H plus 2 Br minus plus SO3, done, makes Br2 plus SO2 plus H2O. That was straightforward, wasn't it? Little note, if you got this 2H plus and 2Br minus, you can, if you wish, write this as 2HBr, but it's not essential. You can just combine these two together. Right, got the idea? I'm going to carry on. Again, if you need another example, listen to this and then do your own, or you can just crack on. Write half equation to convert zinc into zinc 2 plus ions. Again, listen to what I'm talking chemistry all the time. Write a half equation to turn, well, VO2 plus. They're called vanadate ions, and this is V2 plus. Right, so I've got 2 half equations to balance. Zinc's balanced, there's no oxygens, there's no hydrogen, so it's just plus 2E minus. This is a 2 electron oxidation. VO2 plus to V2 plus. Okay, vanadium's balanced, oxygens don't, so 2H2O. 4 hydrogens, so we need 4 H pluses. Now then, this is 4 plus, this is 5 plus on this side, and this is 2 plus on this side. So I'm going to need 3 electrons here. Please, you can do a little check. If on one of the half equations the electrons are on the right hand side being lost, they must be on the left hand side of the other half equation. All right, I've got 2 electrons and 3 electrons. I'm going to times this one by 3, times this one by 2. I'm going to write the numbers over the top so I don't make any mistakes. 3, 3 and 6, 8, 6, 2, 2 and 4. Right, I'm going to combine these. 3 zincs, 8 H pluses from acid, 2 VO2 pluses, 3 ZN2 plus, 2 V2 pluses, 8 H2Os. Any checks or any cancelling? No, that's good. Getting the idea? I hope so. While I'm here, I'm just going to do this. So pause, just think, just for a sec. I could just do a little bit of oxidation phase practice here. Zinc, 0. H plus, +1. Oxygen, -2. The vanadium, -2, -4. The vanadium's got to get me back up to +1. The vanadium there is +5. Zinc 2 plus, +2. Vanadium 2 plus, +2. Hydrogen +1, oxygen -2. If you notice here, the vanadium has gone from +5 to +2. The oxidation state has gone down. That is called a reduction because it's gone down. The oxidation state has gone down. Now I'm looking for something that's gone up. Zinc. Zinc went from 0 to +2. That's oxidation. So just bear that in mind. That's something linking in oxidation states. All right, 3 more to do. Done a lot of talking, but this is you can use these to check your answers then. All right, MnO4 minus into Mn2 plus, SO32 minus into SO42 minus. Okay, 4H2O, 8H plus, 5E minus. So balance that one a lot today. SO32 minus, SO42 minus. Sulfur's balance is going to balance the oxygens. H2O on this side. 2 hydrogens, 2 H pluses on this side. Before I balance with electrons, I'm noticing the electrons are on the left, and the top one, they're being gained, that's a reduction, so they're going to be over this side. Right, this side currently is 2 minus, this side is 2 minus and 2 plus 0, so I need 2 minuses on this side, 2E minus. Right, 5E minus, 2E minus, so if one of those, we're going to times this one by 2, times this one by 5. That's going to be 16, 10 electrons, 2 MnO4, 2 of these, 8 of these, 5 waters, 5 of them, 5 of them, 5 times 2, 10 H pluses, 10 electrons, so the electrons cancel. Right, 16 H plus, 5 H2O, you can put these in any order, 2 MnO4 minus, 5 SO32 minus makes 2 Mn2 plus. Loads going on here. 8 H2O. 5 SO42 minus 10 H plus. Right, I've got some jobs to do here. 10 H plus on this side, 16 H plus on this side. Squibbly dibbly dibbly. 6 H plus. 5 H2O on this side, 8 H2O on this side. That's becoming a thing. I'm going to say that. All right, deal with it. That means there's going to be 3 H2Os on this side. All right, took a bit of work, but it's 6 H plus, 2 manganate ions, 5 sulfur trioxide ions. What would you call them? Sulfate. What do you call them? What is it? Sulfate 4 ions. Manganate 2 plus. Anyway, there it is. Lots and lots of cancelling out. Ooh, I like the look of this. Biologists, you should like the look of this. That'd be glucose, that. C6H12O6. Isn't that known as a reducing sugar? By the way. Makes CO2. Glucose, turning into carbon dioxide. ClO3 minus turning into Cl. Right then, I'm going to enjoy this one. Carbons. Let's balance the carbons first. 6 CO2. Oxygens now, I've got 12 oxygens this side and I've got 6 oxygens this side, so I'm going to need 6 H2O on this side. Looking familiar, by the way. Now I've got 12 and 12 hydrogens, that's 24 hydrogens on this side. That is right, isn't it? So I'm going to need 24 H pluses on this side, and that means I'm going to need 24 electrons on this side. Wowzers. So it looks like when glucose turns into carbon dioxide, it loses 24 electrons. It gets oxidized by 24 electrons. Because it gets oxidized, biologists know it as a reducing sugar because it reduces other things. That is something we're going to come on to. All right, this is the half equation of the glucose turning into carbon dioxide. 24 electrons getting transferred. Anyway, let's do the next one. Chlorine's balanced oxygens are going to need 3 H2O, 6 H pluses, 6 H pluses. Right, electrons. So they're going to be on this side, aren't they? So there's 24 of them over there. 6 H, 6 plus, 1 minus, that's 5 plus on this side. So that's A. Oh, Cl minus. Phew, I knew that I wasn't working. I was going to have 5 electrons and 24, and they don't go well together. Right, this is 5 plus, this is 1 minus. How do you get from 5 plus to 1 minus? You're going to need 6 electrons on this side. 6 and 24 go into the same number, so that's quite nice. 6 and 24. And if I multiply everything by here, by 4 on this equation, it will work. That'll make 24 electrons, 24 H pluses, 4 ClO minuses, 4 Cl minuses, and 12 H2O. Right, let's get cracking. 6 H2O plus C6H12O6, done. Plus 24 H pluses plus 4 ClO3 minuses. Turns into 6, I've done everything there. 6 CO2s, done. 24 H pluses, done. 4 Cl minuses, done. 12 H2Os, done. Cancel time. Right, 6 H2Os, 12 H2Os, get rid of them. Turn this into 6. Done that one. 24 H pluses, 24 H pluses, squibbly dibbly dibbly, squibbly dibbly dibbly. Looks a bit messy, but the overall equation is C6H12O6 plus 4 ClO3 minus makes 6 CO2 plus 4 Cl minus plus 6 H2O. I don't like the look of this 6, so I'm going to make it look better. Some of you need to take note of that. The examiner needs to be able to read your work. Right, I'm nearly there. Good these, aren't they? I can sense even into the future that some of you are shaking your heads at home. How dare you? They are good. They really are. Right, I'm going to go purple pen. Don't know why. Just wanted to. Right, Cr2O7 2 minus. It's called a dichromate ion. Some of you will be looking at this in organic chemistry at a minute. Acidified potassium dichromate, for example. This is orange. This is green. And here's an alcohol. CH3CH2OH. Oh, this really links into Dr. Patel's side of the course. I hope some of you are nodding along with that because you're doing oxidation of alcohols. Here is dichromate. Dichromate is a very good oxidizing agent, but I'll tell you why in a sec. This is an alcohol being oxidized to a carboxylic acid. So we can use half equations here. This is cool. Right, Cr2O7, 2 chromium's going to need to put a big 2 there. 7 oxygens, so that's going to need 7 H2Os. That's going to need 14 H pluses. And this is going to need 6 E minuses. Because there's 6 plus on this side and 12 plus on this side. 6 E minus, not 9 E minus. Notice there are 2 3 pluses on this side. All right, this one then, you might think, how do you do it with organic chemistry? Don't change a thing. 2 carbons on this side, 2 carbons on this side. Let's balance oxygens with water. There's 1 oxygen here, there's 2 oxygens here, so I'm going to put plus H2O. Hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. So we need 5, 6, 7, 8. 6, 7, 8. 1, 2, 3. 4 H plus. Even before I'm going to balance this with electrons, I know the electrons are on this side over here, so they must be on this side over here. 4 H plus, you need 4 electrons on this side. All right, what we're going to do now then, they're balanced. These are half equations that have been balanced. So I can now write an overall balanced equation. This is really useful. 6 and 4 both go into 12, I believe. I'm going to times everything in that by 2, times everything in that by 3. All right. 2 times 14, 28. 2 times 6 is 12. 2 of them, 4 of them, 14 of them. 3 waters, 3 of these, 3 of these, 12 of these, and 12 of these. Right, I'm ready to go. So, 28H plus, not that. Plus, I'll write the waters next. 3 H2Os. It doesn't matter what order you're doing them, as long as you don't miss anything. Plus 2 Cr2O7 2 minus, done that. Plus 3, what's that called? Ethanols. CH3CH2OH makes 4 Cr3 pluses plus 14 H2O plus, I'm going to go on to the next line, 3 ethanoic acid CH3COOH plus 12H plus. bit of a sore arm while I'm doing all this writing. Let's cancel out the H pluses. 12 on this side, 28 on this side, so that leaves 16 H pluses. Waters, 14 H2Os. 14 H2. This looks. Where's that gone? That's looking alright. 14 H2Os, 3 H2Os. So that's going to be, get rid of that. 11 H2Os is peculiar to me. I might have made a mistake here, but I'll have to wait and see in a second. Looks alright. 11 is just unusual. Let me just do a little check. I'm going to count my hydrogens. 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. 1, 2, 3, 4, 5, 6. There's 3 of them, so that's 18, 28, 34. It balances. Cool, there you go. So, in organic chemistry, you've learned that if you want to oxidize ethanol, you need acidified potassium dichromate. Look, you need acidified, there's the H plus, and there's dichromate. I haven't included the sodium or the potassium. Either of those would do. It would be Na2Cr2O7, which is the same as saying Cr2O7 2 lines. I hope that's interesting to you. It should be, because you're doing A-level chemistry. Right, make sure that you've done them, marked them, brought any questions with you to the lesson. We've now got our final sheet to do, which is redox reactions or not. If you like, go and get yourself a little cup of tea. There you go, I'm going to draw a cup of tea, just because I feel like it. Go and get yourself a little cup of tea. Have a break. That was only a 30-minute lesson. It would have taken you a lot more time, but we're now on to this last little bit. I'm going to pause the video and go and have a cup of tea, and then I'm going to come back and finish it off. Right, I'm back. So what we've got is this final sheet called redox reactions or not. How to spot a redox reaction, and we're also going to learn some vocabulary. Right, we already know that oxidation is loss of electrons and reduction is gain. That should be clear with you. There is another little bit of vocab we need. It says here, in any reaction where one species is oxidized, the other must be reduced. We've been practicing this. Both reduction and oxidation take place, so they're called redox reactions. Again, should be fine. Oxidation is loss of electrons, reduction is gain. We're going to look at these now, oxidizing agents and reducing agents. An oxidizing agent is a species that removes electrons from another. An oxidizing agent, there's a nice way of thinking about this. Oxidizing agents, there's two things I want you to think. Oxidizing agent oxidizes other chemicals. I am an oxidizing agent, I am going to oxidize you. I am a travel agent, I'm going to send you on your travels. I don't travel myself. All right, oxidizing agents oxidize other chemicals, but also oxidizing agents, so they remove electrons from another. Now, if you take electrons off something else, you actually gain electrons yourself. So I want you to remember this. This is the crucial one. Oxidizing agents get reduced. They do. All right. If I was an oxidizing agent, imagine this. I'm going to oxidize you. All right, so this is you now. I'm going to lose electrons, aren't I? Yes, you are. The oxidizing agent will take your electrons away. Oxidizing agents get reduced. Please remember that. Oxidizing agents themselves get reduced. Reducing agents gives electrons to another thing. Watch this, I'm going to give electrons away. Here you go. What happened to me? Yeah, reducing agents lose electrons. Reducing agents get oxidized. Now, you might, we're going to repeat this again and again in lessons, but reducing agents, they reduce other species. But remember this, it's more useful this way. Reducing agents get oxidized. Please practice that. Say it to yourself. Reducing agents get oxidized. All right. So, what we're going to be doing in this little activity is you're going to be given equations and you're going to be asked firstly, is this a redox reaction? And you'll notice here, I know it's already done it, but what you do first is you go through the oxidation states. 0, +1 is the hydrogen, chloride is -1, magnesium is +2, chloride is -1, hydrogen is 0. What you're then looking for is for any changes in number. The hydrogen goes from +1 to 0. If that number has gone from +1 to 0, it's gone down, it's got smaller. This is reduction. If the oxidation state goes upwards, 0 to +2, this is oxidation. All right. So what I'm now going to do, I'm going to look at each of these species and find out what has happened to it. All right. The magnesium has been oxidized. The magnesium has been oxidized. Reducing agents get oxidized. The magnesium is the oxidizing agent. All right. The hydrogen in HCl, gets reduced. All right. So what we do here is we circle the whole chemical. This whole chemical here, HCl, was my oxidizing agent. Now I know technically it was the H plus that turned into H2, but we tend to say in there's a mistake here, by the way. There's a mistake there. The H plus in HCl takes away electrons. We tend to say that the chemical as a whole, the HCl, is the oxidizing agent. Please bear with me on this. When you get see a few examples, you'll get it. In any sort of redox reaction, there's something that lost electrons and something that gains. The thing that got oxidized is the reducing agent. The thing that got reduced is the oxidizing agent. We're going to see the activity. You'll get it in a minute. All right. Next little thing, and please, you have to have covered this. There is a special type of reaction out there where you will see one element get oxidized and reduced. Now, it's not as weird as it sounds. If we look at this equation here, you've got chlorine, the element, oxidation state 0. You've got hydrogen that's +1, and you've got oxygen that's -2. Over this side, you've got chlorine -1, and in this chemical, you've got chlorine as +1. So what we can see here, you start off with chlorine Cl2, like this, where the oxidation state is 0. And then one of the chlorines in that Cl2 ended up in Cl-, like this. So here we go, there's Cl2, you've got like that. One of them has ended up as a Cl-, and one of them has effectively ended up as a Cl+. All right. So when you have a situation where one element ends up in two different oxidation states, this is known as disproportionation. All right, you're going to see it happen in real life. So this is something that you need to be aware of. Don't come in here next week not knowing what disproportionation means. Right, so if you're watching this in the future, somebody's just come in. Hello, Gabriel, for coming in. Nice to see you. I didn't get to chat to you because I was busy doing this. That's going to be weird when you're watching this back, isn't it? Right then, what we've got on the bar is we're going to quickly decide whether it's redox or disproportionation. All right, I'll show you how I do it. I'm going to do oxidation states. I'm going to decide if it's redox first. Okay, oxygen -2, that means the sodium must be +1. Oxygen -2, the hydrogen's +1. Hydrogen in this compound is +1, oxygen is -2, sodium is +1. Does anything happen to the sodium? +1 to +1? No. Does anything happen to the oxygen? -2 to -2? No. Hydrogen +1 to +1, oxygen, not redox, therefore don't need to do anything. The oxidation state of the elements do not change in this reaction. Sodium oxide plus water is not a redox reaction. All right then, oxygen elements 0, oxygen in a compound -2, there's 2 of them, the sulfur here must be +4, sulfur +4. On this side, oxygen is -2, the sulfur must be +6. I know I'm quick. All right, you will be slower than this. So, is it a redox reaction? Yeah, the sulfur goes from +4 to +6. I just need to check, something else must have changed. Oh yeah, this oxygen here goes from 0 to -2. It is definitely redox. Is it disproportionation? Is it one element doing both the oxidation and reduction? No, this is sulfur doing it, this is oxygen doing it, so it's not disproportionation. All right, what is the species that has been oxidized? All right, oxidized is when the oxidation state goes up. +4 to +6, +4 to +6. All right, the species that's been oxidized is the SO2. That has been oxidized. It's turned into SO3. If I was being more specific, it's the sulfur in oxygen. The sulfur in this has gone from +4 to +6. But all we need to do is say, you can say there it's the sulfur dioxide that has been oxidized. That is absolutely fine. All right. This oxygen has gone from 0 to -2, so it's the O2, this chemical, that has been reduced. All right. This chemical has been oxidized because the sulfur changed from +4 to +6. This chemical, the oxygen, has been reduced from 0 to -2. All right. The oxidizing agent is the thing that got reduced. That almost rhymed. So all the O2, O2, SO2, SO2. The reducing agent is the thing that got oxidized. By the way, that column's always that column, that column's always that column. I do believe. Right. I'm going fast now, nearly the end of school. So, NaBr +1 -1, H2SO4 +1 -2 for oxygen, sulfur is +6. Na2SO4 +1 for the sodiums, oxygens are -2, sulfur's +6, HBr +1 -1. Nothing changes, not redox. All right, KBr plus F2. This is halogen displacement, fluorine displacing bromine from its salt. Potassium +1, bromide -1, fluorine 0, bromine 0, potassium +1, fluorine -1. Right, the bromine has gone from -1, bromide, to bromine. The fluorine has gone from 0 to -1. Okay, so it is redox. It's not disproportionation because it's not one element doing the oxidation and reduction. I've got bromine and fluorine. You'll see disproportionation in a minute. Right, the species oxidized. So I'm looking for one where the oxidation state has got more positive. So -1 to 0, -1 to 0. That's the bromide turning into bromine. So it's the KBr. KBr is the species oxidized because that contained the Br minus. All right. Species reduced, F2, because it went from 0 to -1. That's getting more negative. Species that gets reduced. So oxidizing agent is the thing that gets reduced. The reducing agent is the thing that gets oxidized, KBr. I want to go home, but I'm trapped doing this. Right, you might remember H2O2 from the start. Hydrogen +1, oxygen -1, bizarrely. It has to be that. Go back to the first lesson. Oxygen on this side 0, oxygen here -2, hydrogen +1. What you'll notice is the hydrogen